26% of the world's population does not have access to safe drinking water. That equates to 2 billion people who are extra susceptible to waterborne disease outbreaks. In 2024, we live in a modern, digitally active world with archaic and slow water safety resources. Nowhere is this more true than in less developed nations. Many Pacific Island nations have powerful communication tools across small communities, yet predictable weather conditions can compromise water supplies, resulting in the increased spread of waterborne illness. The problem is that the only way we can manage outbreaks is to sit and wait for the outbreak to occur. Wait for the information to reach a governing body or humanitarian group, and then finally send help accordingly. This can take weeks or months, and the impact of an outbreak is felt immediately. But what if instead of being reactive in the face of a waterborne disease outbreak, we could be proactive? Imagine if we could tell exactly where the next outbreak is going to be, exactly which communities are the most at risk, and even have the power to reshape water infrastructure in the most optimal, affordable, and sustainable way. Imagine if we could not only predict which disease is most likely to affect a certain area, but we could provide treatment even before a disease like cholera can claim its first victim.
This is exactly what our proposed solution, HydroSafe Analytics, allows us to do, supporting Sustainable Development Goals SDG 6 and SDG 6.1. Our service highlights areas of high risk of water contamination through accurate predictions, empowering communities to take preventative measures by providing educational resources and facilitating the effective allocation of local and government resources. This is how our service works. It all begins with collecting data from communities. The data is then combined with publicly available weather and geodata in the pre-processing stage. The refined data is then fed into our predictive model that analyzes and determines communities at risk of water safety issues. The model churns out predictions and flags any areas that need attention. These results are then used by governments or NGOs to send the right resources like clean water supplies and purification tools to the places that need them most, and allow for local communities to prepare for any possible outbreaks and put preventative measures in place.
The model is shown here with an example of some of the data we will use. From our peripheral devices, we collect information about how many users are sick, qualitative observations of the water such as any changes in taste and color, and the type of water source. We also use the broader network of users to see if nearby communities have high rates of illness. From the World Health Organization, we take historical health data and merge this with public, geographical, and weather data. We then feed this data into our analytical models. The Outbreak Notifier uses simple statistical analysis to detect an outbreak after it has occurred, looking at significant spikes of infection correlated with water sources and common symptoms. The logistic regression model takes in the data, outputting the probability that a given water source is contaminated. It checks its prediction later against the Outbreak Notifier to retrain and improve model quality. This can additionally incorporate laboratory testing to validate the predictions made. The multi-class logistic regression model functions in a similar way, taking the same inputs and using laboratory test validation to predict the likely source of contamination. This can be used to suggest how people can decontaminate their water and steps that could be taken in the future to avoid this kind of contamination. Logistic regression models, whether they have a single output or multiple, determine the probability of a given data point having certain attributes. They do this by taking sample data points and finding an optimal mathematical model, such as with a neural network trained by backpropagation, that best explains the given data. Outputs are constrained between 0 and 1 using a scaled sigmoid curve, which can be easily interpreted as the probability of the chosen attribute being true, which is how both our single and multi-class logistic regression models work.
The HydroSafe service is designed to be universally accessible to everyone. Initially, the service will be restricted to areas with mobile coverage. However, as our database grows, we'll be able to expand our reach to neighboring locations by extrapolating our predictions to areas with limited data. The main expense of HydroSafe is the initial development and maintenance of our predictive model, which can be funded by government services and aid groups. To enhance the accessibility of our solution, HydroSafe is designed to be affordable for the end user. The service is free for everyone with access to a mobile device through our intuitive user interface. For those without smartphones, the service is available via SMS and phone lines.
We have a 5-stage timeline planned, going from the initial development and exploratory analysis of our model to model deployment in suitable areas before expanding our reach to areas with less digital technology access, using other communities as examples for the model. By implementing the HydroSafe cycle, we can make a significant impact on water quality and public health by improving water quality reporting and decreasing waterborne disease outbreaks. Through targeted resource allocation and advanced predictive analytics, we can effectively manage and prevent outbreaks. Additionally, by involving and educating communities, we empower them to be proactive in ensuring their water safety. Together, these efforts lead to healthier communities and a safer, more sustainable future.